Hey everyone, have you ever looked at a chemical reaction and just wondered, where is this all going to end up? It's kind of like a puzzle, right? You mix a few things together and they start to react. But what will that final picture actually look like? Well, today, we're unpacking the systematic framework that lets us solve this puzzle every single time. It's called the equilibrium algorithm.
So that really is the big question, isn't it? How do chemists do it? Is it just a bunch of guesswork, some kind of chemical intuition? Turns out, it's not guesswork at all. There's a powerful, step-by-step method to predict the exact composition of a reaction mixture once it settles down. And that's what we're going to master in this explainer. So let's dive in.
You see, the secret isn't some kind of magic. It's a method. The best way to think about it is like a reliable toolkit, or maybe a 5-step assembly line for solving any equilibrium problem you run into. Once you know the steps, you can tackle pretty much anything.
And here's that very pipeline. It all starts with Station 1, the input, which is where we write down our balanced reaction. From there, we move to Station 2, the grid, where we map out all the changes. Station 3 is syntax. That's where we build our equation. Station 4 is compute, where we solve for our unknown. And then finally, Station 5, the output, where we calculate our final answer. It's literally a roadmap from the problem to the solution. And, while every station is important, the real command center for our calculations is Station 2, the grid.
Okay, so let's get into it. This right here is the ICE grid, and it is brilliant because it organizes all the chaos. ICE stands for Initial, Change, and Equilibrium. The I row? That's simple. What are your starting amounts before anything even happens? Now, the C row is where all the action is. It represents the change as the reaction moves towards equilibrium. We use the variable x here to represent the amount of reaction that happens. Reactants get used up, so they're negative, and products get made, so they're positive. And you got to notice that stoichiometry multiplier. That number comes directly from your balanced equation, so if a product has a 2 in front of it, its change is going to be plus 2x. Makes sense, right? Finally, the E row for equilibrium is just the sum of the first two, initial plus change. This grid is everything.
All right, let's put this into practice with our first case file. For this one, I want you to think like a detective. In these types of problems, we're given clues about the final scene, like the total pressure at the very end, and our job is to work backward to find the culprit, the equilibrium constant, K.
So here's our case. The mission? Calculate Kc and Kp. The system? Dinitrogen tetroxide, N2O4, is turning into nitrogen dioxide, NO2. So, what do we know? We know we started with 13.8 grams of N2O4 and that the final total pressure in the container is 9.15 bar. The unknowns? The equilibrium constants themselves. Let's get to work.
First things first, our data needs to be in the right format. We have a starting mass, but our final clue is in pressure, so we need a bridge to get from one to the other. That bridge is the ideal gas law. As you can see, we start with our 13.8 grams, convert that to 0.15 moles, and then we plug everything into the equation. This gives us our starting pressure, 4.98 bar. That's the first piece of our puzzle.
Now, let's see how this fills out our grid. We drop that 4.98 bar right into the initial box for N2O4. We didn't start with any product, so that's a 0 for NO2. Now for the change row, some amount x of our N2O4 is going to react, so we write minus x. And because the stoichiometry is 1 to 2, we're going to form plus 2x of NO2. This means our equilibrium row is just 4.98 minus x for the reactant and simply 2x for the product. See how that works?
And here's the big breakthrough moment. Remember that clue? We know the final total pressure is 9.15 bar. Well, that total is simply the sum of the pressures in our equilibrium row. So the pressure of N2O4, which is 4.98 minus x, plus the pressure of NO2, which is 2x, must equal 9.15. With this one simple equation, we can solve for x, which turns out to be 4.17. From there, we just substitute that value back in to find the final pressures of each gas. And then we can calculate our Kp. And boom, case closed on Kp. It comes out to 85.87.
But wait, the mission was to find Kp and Kc. Luckily, these two are related by this super handy formula. Think of it as our translation engine. Kp equals Kc times RT to the power of delta N. Now what's delta N? It's just the moles of gas products minus the moles of gas reactants. For our reaction, that's 2 minus 1, which is just 1. We plug in our known values, solve for Kc, and we get our final answer, 2.6.
Okay, time to switch hats. We're no longer detectives looking at the past. We are now fortune tellers, predicting the future. In this second type of problem, we're given the equilibrium constant K, and we have to use its power to predict the exact final state of the reaction. Here's our next mission. We're starting with 3 moles of PCl5, which is going to decompose into PCl3 and Cl2. This time, what we know is the initial amount and the value of Kc, which is 1.80. The unknown, the exact final concentrations of everything in that mixture. We are literally predicting the future composition.
We start the exact same way, with an ice grid. Initial is 3 for PCl5, 0 for the products. Change is minus X for the reactant and plus X for each product, since the stoichiometry here is all 1-to-1. Now we build our Kc expression, products over reactants. When we substitute our E rho values into this expression, we get x squared over 3 minus x equals 1.80. A little bit of rearrangement and, well, we have a quadratic equation.
So to solve this, we've got to use the quadratic formula. But here's a really critical step. Math gives us 2 possible answers for x, one positive, one negative. This is where we have to apply what I call the chemical reality check filter. Think about it. Can you have a negative concentration of a chemical? No way, of course not. That's physically impossible. So while the math gives us 2 roads, only one leads to a place that actually exists in the real world. We have to discard the negative answer and move forward with the one that's physically meaningful. X equals 1.59.
With our valid value for x, we can now calculate the final concentrations of all 3 species. PCl5 will be 3 minus x, and the products will both just be equal to x. And here's the final crucial step, verification. We take these calculated concentrations and plug them back into the Kc expression. And would you look at that? The result is 1.793, which is basically a perfect match for our given Kc of 1.80. Our prediction was accurate.
So, we've gone through 2 very different case files, the detective and the fortune teller. Now, let's zoom out and combine them into a single, unified master plan that you can use for any problem that comes your way. This slide really lays it all out, side by side. Archetype A, the detective. You're given the initial and final measurements, and you're missing K. The math is usually simpler, often just linear. Archetype B, the fortune teller. You're given the initial state and you're given K, but you're missing the final concentrations. The math is a bit tougher here, often leading to those quadratic equations. Just recognizing which pattern you're looking at is half the battle.
And here it is. This is the single most important takeaway. This is the equilibrium decision tree. This is your master plan. You start at the top, read the problem, and just ask yourself, what am I given? If the problem gave you physical measurements at equilibrium, you follow the path on the left. If it gave you the equilibrium constant K, you follow the path on the right. This flowchart will guide you step by step from the question to the answer, every single time.
Finally, let's just do a quick review of the 2 key formulas that power this entire process. We've got the general expression for K itself. It's always the products raised to their powers divided by the reactants. And we have our translation engine, that formula that connects the world of pressures, Kp, with the world of concentrations, Kc. These are the core tools in your new toolkit.
So there you have it. You're no longer just looking at a reaction. You are now equipped with the algorithm to understand its destination. You've got the grid, you've got the detective work, the fortune telling, and the master decision tree. The only question left is, now that you have the algorithm, what chemical future are you going to predict first?